general physics. I hope everyone is all right, as one can be with the atrocities going on in the war, during the war in Ukraine. It's a terrible situation. Nevertheless, we are still required to have our lectures, so we continue. As a matter of fact, today we need to continue discussion of dynamics in regard to what I've been doing recently. Probably we have made some formal introduction. I'm not sure if we have elaborated on Newtonian laws of dynamics. We refer to inertial systems. We had introduced the motion equation, which is a second order differential equation for position. And we also mentioned the law of action-reaction regarding reciprocation of forces. So one force acting on one object is reciprocated and acts on another object with the same value but oppositely directed. Right, and I'm not sure if we have managed to solve the second law of equation for simple cases. Generally, this is what we will be focusing on today, at least if we had managed with solving simple cases than for somewhat more advanced cases. The first case we would refer to as uniform motion with force being equal to 0. With force being equal to 0 means that also acceleration is equal to 0. From that it follows that since acceleration is derivation of velocity per time, then velocity vector is constant, meaning that there is one direction of a vector which doesn't change in time, doesn't change its direction, doesn't change its length. This is constant velocity, so v0, and therefore one can set the axis for the consideration of this motion in one dimension along this vector, right? And in that case, for one-dimensional consideration, we will have v0 being constant, but we can call this v, but at the same time, v is derivation of position upon time. However, position r is a vector of 3 coordinates. So in one dimension, that would be for example, of x, derivation of x upon time, meaning that dx is equal to v dt, and this can be integrated both sides from x0 to x, from time 0 to t. That would mean that it would be x minus x0 on the left is equal to vt minus t0. So x is equal to vt if x0 and t0 are 0. Right, I'm not sure if we have done that. Even if so, that short revision of it won't hurt. So let's go to now second case, which we refer to as uniformly accelerated motion with force acting being constant. So what it means that acceleration therefore is constant. It is equal to force divided by mass, and therefore it is a vector, right, not changing direction and also not changing magnitude. So a is equal to dv over dt, and again in similar manner one can limit the consideration for one dimension actually without losing generality of this consideration, because all these equations are linear. So if we solve one equation for one coordinate, then we can generalize the result for the remaining two coordinates, and three equations for three coordinates is basically the same as a vector equation, because this vector equation, for example, resolves to maybe here to such equations: ax is equal to dvx over dt, ay is equal to dvy over dt, and az is equal to dvz over dt. The linearity of vectors makes sure for that. So as I mentioned, reducing consideration to one dimension does not limit generality of the consideration of the result. Okay, so for one dimension, what we will deal with is a equal to dv over dt. And again, a multiplication by dt means that we would have maybe dv on the left and on the right a dt, with the integration, which is required as an opposite operation to derivation. We will go from v0 to v and from t0 to t. Okay, excuse me for a moment. I'll look into the. Okay, I see that some of you have joined because I have postponed the beginning of this lecture due to the necessity of sending out the invitations for the second part of the group, which normally has this course in Polish, but due to some further considerations, for now at least, we are having this lecture jointly within those two groups in English. So again, sorry for that late sending of the invitations. Hope you may manage to connect now. So I see there were some 15 persons, 15 students previously. Now we have more than 30. So it means that the second group has successfully joined. Well, what I was saying in terms of introduction to this lecture, that we continue dynamics. Today we will move on to consideration of a little bit more advanced cases for the second law of Newtonian dynamics. Just to make sure that we are on good track, I would like to ask you to maybe make some short review. Perhaps some of you remember what we have been doing the 2 weeks ago. In my view, probably we didn't go into solutions of the second law of Newtonian dynamics, but I might be wrong. Even if we did make some solutions, then probably they were limited to those two cases that I now briefly remind you: the uniform motion and the uniformly accelerated motion. Now, to be sure that we know what we are talking about here is this second law of Newtonian dynamics. The first one was that inertial systems exist, which is quite problematic because we mentioned that normally we can't really find any system that is under no acceleration, right? Earth itself, which seems to be stationary when we fix our reference frame to some street building or whatever is standing still on Earth, it's just an illusion that it's a stationary system, because of course we know that the Earth rotates. It also moves along the trajectory orbiting the Sun. So different accelerations are actually affecting the reference system, which is fixed to the surface of Earth. But these accelerations are not very large. I mean that, of course, we can do experiments, and I mentioned, for example, the Foucault pendulum, which during some certain number of minutes will deviate from its original plane of oscillation. But these are pretty small effects, so we don't really feel much of these forces, which we refer to inertial forces, in reality. However, there are some interesting practical problems. For example, you realize that due to the rotation of Earth, when you would stand on the equator, of course, not even on the equator, everywhere actually, but on the equator, this would be most pronounced effect, because then the rotation velocity would be highest in terms of the velocity vector from the consideration of this Earth rotation around its axis. And then due to such effects, with also a proper alignment of the vectors of the forces, inertial forces of the, we refer to this force as the centrifugal force, right? If we have, for example, some system that is undergoing motion over a circle, there is a radius of the circle, then due to this acceleration, that his velocity is always tangent to the trajectory, which is circular by our assumption, then it means that the acceleration that causes this velocity vector to turn so that it is tangent in all positions, so of the circular trajectory, it must be turning constantly, right? Then we refer to this as a centripetal acceleration, AC, centripetal acceleration, which is always normal to the velocity and is therefore parallel with the radius of the circle. Sure. Because of the fact that this is a reference frame that is undergoing this acceleration, this AC acceleration, centripetal acceleration, then if you assign your reference frame like this with this object that moves under this acceleration, this object that makes a circular motion, then this reference frame is under this acceleration. And since it accelerates with this acceleration, then there appears inertial force, which is directed oppositely. It is the D'Alembert inertial force. And also this inertial force is associated with inertial acceleration, which is referred to as, it is force divided by mass is this inertial acceleration. And we refer to this also but not petal like this one, it's centripetal, and this is centrifugal acceleration. It's an inertial acceleration. So the one you would feel when you are in the such a high G wheel device, when you, for example, pilots of fighter jets are trained in or examined how many Gs they can withstand, and within these accelerating circular moving capsules, such accelerations, which are centrifugal in nature, can be achieved with magnitudes, for example, exceeding few Gs, up to maybe 9G, which is generally considered as a human limit to withstand high G, after which consciousness is usually lost. So what I'm referring here to is that Earth is similar in that regard, that because Earth is rotating, then a person standing on the equator, for example, or actually in any other position of Earth, will undergo centrifugal force, which is, of course, directed upwards from the surface of Earth, right? Because we would be, when a person stands on a given place on the surface of Earth and the Earth rotates, that means that this person is undergoing a circular trajectory motion, right? And this force, which is centrifugal, would act opposite to the direction of the gravity, right? On the equator, that would be the case. However, in the case of other points towards poles of Earth, this would diminish because gravity would always, the vector of the gravity force or gravity acceleration would be always directed to the center of Earth, while this acceleration would be always directed perpendicular to the axis of rotation. So only increasingly smaller component of this acceleration, centrifugal acceleration, would be acting directly against the gravitation if you move from the equator towards the pole, right, in terms of the geographical latitude. And what can be taken out of this such conclusion? So an interesting question, maybe of kind of, let's say, practical calculative problem, is to ask how fast or maybe how long the day should last, day and night, which we understand is 24 hours. So how much shorter it should be, so that the Earth rotation would be enough, would be sufficient to overcome with the inertial force, centrifugal force, the gravity, meaning that the force, centrifugal force, would be such big on the equator that people would be ejected away from Earth. And such calculation can be done, and actually basing on this, right, on the following equation here, maybe on the margin, I will write it down, that you have normal acceleration, which we had considered in the normal reference frame. I think we did manage to finish the normal reference frame, is it correct? Normal reference frame, we had acceleration. Normal acceleration was a mass without mass, because there would be force. So normal acceleration was v squared over r, and that was on the centrifugal force, centrifugal acceleration as well, in case of the motion over a circle, and that should be equal to the gravitational force. So force of the gravity should be equal to the centrifugal force, meaning that mg should be equal to v squared over r, where r is, of course, the radius of Earth. You can also find the connection between omega and v, that omega is v over r, or otherwise v is omega r, which means here that you can change this to actually omega square r, because it would omega square r squared, but one r is cancelled with the denominator. So that means that omega square is equal to mgr for this situation to appear that centrifugal force is balancing down the gravity, meaning that omega, the angular velocity, should be equal to the square root of mgr. In other terms, omega is 2 pi, the total angle in radians, so 360 degrees, divided by the temporal period, which for Earth rotation is 24 hours. So again, one can make here a substitution, which would be t is equal to 2 pi over square of mgr. Oh, and probably mg has cancelled here as well, because here we would have mass, because it's force, which is multiplication by mass. So masses would cancel, and I would not have mass anymore here. Mass is not present. So it will be just 2 pi over square root of gr. And it's pretty simple to calculate, because r is about 6,400 kilometers, g is about 10. So it's like 6 multiplied by 10 to 5. And 2 pi is close to, say, maybe 7, something like maybe 6.5. So it's square root 6 divided by square root by 10 to 4, maybe 10 to 5. Okay, because so if we would to make it more clear, the period t is around 6 divided by, again, 10 multiplied by 6,000 kilometers. So I would have here 6 multiplied by 10 to 4. Okay, and that would be 10 to 4 is 10 to 2 without, something like this. And here I have 6 divided by square of 6, something like this. Right, is it correct? I'm not really sure here. Maybe. Well, now let's maybe not focus on proper calculation of it, because I'm not sure if we're not missing something, but from what I can remember, I calculated it some time ago, it was about 1 hour, so, or something even more, that's more close to 2 hours. that would be a consideration of how fast the Earth would rotate, and what should be the duration of the day and night together. So it should be about maybe 2 hours, something like this, maybe a little smaller number of minutes would be enough for the centrifugal force to balance down the gravity. Yes, and the conclusions here, of course, are maybe just to illustrate the importance of inertiality. Nevertheless, we mentioned also that these laws only hold for inertial systems. However, if the system departs inertiality, one can readjust it by kinetical types of corrections. And these are these non-material inertial forces that can be introduced somewhat artificially to account for these accelerations that are properties of the reference frames. Right. So what we should do further on is continuing consideration of the uniform motion has been done. This is the result for the uniform motion. Generally, what we address to equations for kinematics, usually we deal, as you know, with these differentials, and the ratios of differentials, like dividing one differential by the other, is by the definition the derivation. So the upper differential is the function, the differential in the denominator is the argument, and the infinitely small increment of the function in lieu of infinitely small increment of the argument, normalized by this infinitely small increment of the argument, is the definition of the derivation. And what do we use derivations widely in kinematics and therefore also in dynamics in regard to answer to what is the force, because the force is the cause of motion when acceleration is multiplied by mass, because these derivatives are simply the measures of how physical quantities that describe motion change. And motion is all about change. It's generally change of the position. This is generalizing understanding on formal notion of what is motion about. That you use a notion of coordinates varying in time. That's the formal idea behind description of motion. And then when this coordinates, spatial coordinates in three-dimensional space, change in time, you of course ask the question how fast they change in time. And this is the measure of first order derivation of the coordinate function, the position vector r, over time. And that is the definition of velocity. Then you may ask the question, okay, the velocity might be constant, it might be also changing. And if it changes, then how fast it changes? And that is, again, mathematically described by the derivation of the velocity upon time. This is the measure of acceleration. And usually, acceleration is the last derivation that is practically used. Of course, as I mentioned, there can be also considered some more further derivatives, for example, derivation of acceleration, which would be referred to as jerk, but it's not used too much, and we simply can omit it. So then, of course, the main other focus after the discussion of some physical properties of forces, which are in general material, this reciprocation of forces is also a very important principle. And it states that forces are material in origin, and that considers, questions such as what types of forces, what types of interactions exist in nature. This we had discussed the last lecture, where we referred to gravitational forces as the most important class. I mean, important in terms of macroscopic scale, because this gravity force is dominating the evolution of universe in macroscopic scale. Then electromagnetic force, which is irrelevant in the macroscopic evolution of the universe, but is very important on our scales in chemical reaction, in structure composition of between materials and so on. So it's also very important. And then to forces which are considered as nuclear forces, not classical interactions anymore. The weak and strong interactions, which are again irrelevant on the macroscopic scales, irrelevant on our scales, and also just working properly in nanoscopic scales, the weak interaction larger scales than the strong interactions, but still at the dimensions of atoms at most, while strong interactions at the dimensions of nuclei of atoms. So, of course, every force of these four fundamental groups is critical for the universe, how it looks on their scales, because we would say, okay, in the macroscopic scales, nuclear forces are completely irrelevant. But if they were not there, of course, atoms would not be bound together, and a nuclei of atoms couldn't also function as they do. So we could forget about normal types of matter, and that would, of course, bring consequences to the large-scale evolution of the universe as well. So these are very important. We mentioned some properties of them, but subsequently we did say that what physics is interested in dynamics are solutions of motion equations. We also mentioned that for complicated systems, this equation holds the principle of determinism, because for a second-order differential equation, only one solution exists, and this is a unique solution. So unique solution gives us this notion of determinism. And then, of course, comes time to make some solutions, and one need to address the question of when it is possible to do it analytically. So whenever the cases are simple, it is possible to solve these motion equations analytically. And the simple cases are starting from the most simple case, this is the uniform motion when the force is zero. That, of course, calls for acceleration to be zero, because the relation is, as you can see here, 1 to 1. So when force is zero, then acceleration is zero as well. Then this leaves us with reversing the operation of the derivation, because since acceleration would be zero, and since acceleration is the derivation of velocity upon time, then it means that velocity is constant. And since of course, why you can answer that the velocity is constant, because it means that derivation of some function must be equal to zero, and the derivation is the function that only of constant is zero. It is more formally, it follows from the integration calculus, because when you have such an equation, you can write that this is actually the dv is equal to a dt. And you can put integrations on both sides, because this is something that we refer to as differential equation of separated variables. And therefore, you can use this separation of variables to your advantage by multiplying both sides of dt. These are, as I mentioned, derivations you treat as division of differentials. You have derivation of velocity upon time, this, and you treat it simple like algebra of differentials, where differentials are treated like normal functions. So you treat dv separately from dt, and you can multiply by dt a cross product. So this is what we do. We use cross product. So dv is equal to a dt. That really means that you multiplied both sides of this equation by the differential dt, and on the right it cancelled by dividing by dt and multiplying by dt at the same time. So in the result you get this, but also remembering that this is zero, so the integration of zero, and the integration of zero, the integration is the operation opposite to derivation, and here you have velocity. When you omit, of course, the limits on the integration, normally you would need to add constant, but it follows also from the fact that you ask the question on calculating integration on what is the function which gives the argument of integration upon derivation. And here the argument of integration is zero, so upon derivation it must be a constant that gives zero, because only constant derived gives zero. So that is consideration. And moving on forward, right, when you have constant velocity, You designated v0, but you can also designate it as vs here. So that is equal to derivation of dx over dt. You can multiply again by dt both sides. You get dx, and this is now in full done when I set the integration limit. So it's integration on x is going from x0 to x, and the integration over dt is going from t0 to t. Yet velocity, we remember, is constant, so it can be taken out of the integration, right? This means that I have here v and integration from t0 to t of dt, and here I gather for x, you should write in more formal way, x in the limit from x0 to x is equal to v t in the limit of from t0 to t. How you substitute limits is probably known to you very well from analysis mathematically, where you calculated limited integrations, and then you have x minus x0. You put first the upper limit, then subtract substitution of the bottom limit. So it's x minus x0, and it's v. Same goes with t minus t0. Right, and that leaves us with very well-known equation that S is equal to Vt, right, or V is equal to S divided by T, where we understand that S is this generalized one-dimensional distance covered. Now, also, I mentioned the comment, maybe because some of you have connected that in regard to this limiting of dimensionality for the consideration, you do not lose generality here. Generalization is preserved and is always possible, because when you refer to vector equations, such as, for example, this one, right, or this one, or whatever, it's the same actually, you have this equation as actually three equations for separate components. We refer here to our considerations in three-dimensional real space. So that means it has three dimensions, and for each dimension, for each component of this regarding this dimension, you need to write your derivation equation. And these can be solved in one of the dimensions, but since they are analogous equations, they can be generalized trivially and also written together in a set. This is equivalent, fully equivalent to writing an equation in 3D. So 1D does not limit the consideration to just 1D. It's a simplification for calculation, but it can be, and generally is, automatically understood as going to more general case of 3D. For the uniformly accelerated motion, it's a second simplest type of situation. Here, force was equal to 0. Here, force is constant. So you see, if it is not 0, then the second case of complexity in terms of the most simple cases is that the force is constant. It's not changing in time. And then from the equation motion, A is equal to force divided by mass, and it is constant because force is constant, mass is constant as well. So that leads to this consideration when we take a one-dimensional case and we omit these designations for axes. They are not very relevant. It doesn't matter which we choose, so we just do not write them. But also we do not write vectors, understanding this is indeed a limitation to 1D. So we have A is equal to dv over dt, and again it's a separated variables differential equation, so you can multiply by dt both sides, and on the left side you have there dv, or maybe more like on the right side, but you change the side, so it is on one side is dv, and again integration goes from v0 to v, and then on the second one is a dt. So similarly as previously, here we get v minus v0, and on the right a is constant, right? So that means that here a is constant still, because it was constant as a three-dimensional vector, so all its components must be constant. So a is taken out of the integration because it's constant, and what we are left is again integration of dt, so it's just t minus t0, so this one. So v is equal to v0 plus a t minus t0. If you set v0 equal to t0 equal to 0, your initial conditions, then the equation becomes very well known. V is equal to at. Now this is velocity, so one needs to continue to consider from velocity, you can consider position. So again, in one dimension, v is equal to dx over dt, or maybe I should write more generally here, ds over dt, not designating that any particular axis chosen, but actually s could be x, y, z, or whatever chosen axis of your reference frame you want. It can be by an arbitrary angle rotation. So we have this, and means that ds over dt is really, maybe we should write the full one, v0 plus at minus t0. And you need to multiply both sides by dt. So integration of ds going from s0 to s is equal to integration of v0t plus integration again t0 to t plus integration of 8t dt from t0 to t, and plus integration of 8t0, which is a constant, from t0 to t dt, something like that. So what do we get from that? Let me maybe try to move on these equations upwards to some extent. Okay, let it be like that. Okay, and what we need to see here is the linearity, of course, of integration operation. Normally here we would have integration on this whole multiplication and sum on the right. However, sum of integrations is equal to integration of the sum, so we can use that for simplicity. So eventually we have s minus s0 on the left is equal to, here we have I can see that it's dt should be here, not t. So it's v0, which is a constant. So it's again t minus t0. So it is v0 t minus t0 plus second one is 8t. So a is a constant, but t is not. T is a function of time, which is integrated here upon. So we have a. And now the question is integration of t dt is what? It's we need to know the function of which derivation gives a linear t. So it would be t squared over 2, because t squared over 2 would be 2t, right, divided by 2. So 2 cancel, and we are left with t. So this is t squared over 2. But this t squared is again t minus t0, because we need to set we need to substitute the limits of the integration. So it's t minus t0 squared over 2. And then the last term is now at0, where t0 is constant. So this is at0 and just t integration of dt. So just integration of dt from t0 to t. So it is t minus t0. So this is it. And eventually, you can see that you can bring it together when you have, for example, here is, okay, maybe let's change it a little bit. This is it. Here we have, this term is quite critical. 80 squared over 2 for the position is well known. And then what we're left with is, here we would have minus at0 squared, but also minus at0 squared half. Yeah, maybe it's not important to change it. This form is probably enough, right? And again, if we simplify it a little bit, like setting maybe t0 equal to 0 and leaving out velocity not necessarily equal to v0, then what we have is s is equal to s0 plus v0t plus 8t squared over 2. And this is, again, quite well-known equation, which is usually given without s0, so it would be just v0t plus it squared over 2. Where v0 is the initial condition equal to 0, then the distance is just at squared divided by 2. Right, and this is, you can see, pretty straightforward solutions with simple integral calculus, which is required to revert these derivations to be able to find, you know, this derivation from, just a second, from a consideration of, for example, velocity to find the position, and from the consideration of acceleration to find velocity, because, of course, acceleration is the derivation of velocity. But when you have acceleration, you do not have velocity. You need to revert derivation, and the reverse of derivation is the relation of integration. So you need to slightly integrate here. Okay, so this is done. Let me now erase the whiteboard, because what we would need to do next is the third case. Still, what we do is solve the motion equation, which is actually the second order differential equation. And by doing that, we are now focusing on the third case, which we did consider f0, we did consider f constant. What is the next class that f can be considered as the most simple? The simplest case is that there is no f. The second simple case is that vector f is constant. The third most simple case is that it is linear. Linear in what? Because these are all functions of position. So linear in position. If it is linear in R, what it means it's linear in R. So f is equal to, if it would be positive linear on R like this, then the motion would lead to infinite values, right? Because force would be increasing with the distance. It's generally artificial. There is no such force that would increase with distance for the universe we know, because if there such forces would exist in nature, then of course you would have the matter dispersed, because we would understand it's a positive force. So it would repulse matter. The physical system would be repulsed increasingly as they are farther away from each other. They would be increasingly repulsed, and therefore, within the evolution through a certain period of time, we would see no physical systems. Right. Actually, this might be a case that we indeed observe such a force in nature, because we know such a fact, which has been hypothesized about, but recently has been confirmed around the change between the centuries, around the new millennium, in maybe somewhere just slightly before 2000. What we have confirmed now astrophysically by astrophysical observations is the increasing or speeding up acceleration of the expanding universe. So we know that universe is expanding, but there were high levels of uncertainties regarding to the pace of this acceleration, whether or not this acceleration is slowing down or it's constant. Now, if there would be a constant, there would be expansion. Yes, there would be still expansion, but maybe constant, without acceleration or deceleration. And finally, the last hypothesis, the acceleration expansion, that the universe would expand in accelerated pace, that the more time flows, the higher would be the rate of the expansion. And it is actually confirmed that the universe seems to be accelerating with its expansion. And this is known as the dark energy, which is huge amount in total matter energy assessment of the universe, which is driving this accelerated expansion. No one really knows what this dark energy truly is. Of course, why it is referred to as dark energy, because it is acting with this expansion type of interaction rather than contraction type of interaction that is a property of matter and gravity. The visible matter that we can account for by simply physically observing large concentrations of matter which are visible is about just a few percent, maybe even about 3% of the total matter-energy balance that is consistent with this observed acceleration of the universe. How this observed acceleration? Okay, maybe before we address that, let us shortly comment on what other are these ingredients in this balance of matter and energy on the universe scale. Furthermore, we have about 30%, including this visible matter, so maybe like 20% more, is for something that we refer to as dark matter. Dark matter is the matter that we know there is this matter because of the gravitational effects that it exerts on other material concentrations like galaxies and groups of galaxies and so on the visible matter. But we cannot make any physical assertion about the nature of this dark matter. It seems to be only interacting gravitationally, and there is no possibility to see it and to interact with it in any way. At least there was a failure in current progress in trying to make some other contact other than gravitational with the dark matter. So it is an open question. What are these dark matter particles? Whether they recently there has been some considerations, quite probable results point out the possibility that this matter is also complexly coupled between dark matter particles, between themselves. So they may create complex structures and so on, but these structures and interactions which are very strong among dark matter, similarly as we have strong interaction between visible matter, they are just decoupled from each other. So although they create structures on their own in terms of dark matter world, there is no interaction, or very, very weak, undetectable so far, interaction between dark matter and visible matter. And this dark matter is actually dominating in terms of at least few times as much there is dark matter in the universe as the visible matter. And what is about this? About 30% of this balance of energy and mass in the universe. If there would be nothing else, of course, this mutual gravitational attraction of the structure of matter and dark matter would lead to a collapse of the universe. There would be attraction increasingly strong as these objects would getting nearer and nearer to each other. So there would be not expanding universe, but a contracting universe in accelerated manner. But since the universe is observed to be not contracting and not even in balance of between contraction and repulsion forces, we see the universe as being expanding with increasing pace. This means that there cannot be just in the balance this matter and dark matter. And what is done to account for this increasingly fast pace of expansion of the universe is the introduction of something that we know there must be gravitationally, actually overcoming the attraction force of the gravitation between all the components of dark matter and visible matter components, but is there to expand them. So it must overcome the gravity, the attracting gravity, and repulse them even higher up to the intensity of the repulsion, up to the strengthness of repulsion, the farther away they are from each other. So they would be consistent with such an equation, so that particles, for example, would be getting far away from each other. They would be repulsed even stronger, right? Because this is how we would understand this. We have our reference frame, two particles here, and maybe one particle is set in the origin of the reference frame, and second particle here. And here is the radius, also not the radius, but the position vector. Now, if they would be repulsing, so that this is the force of the repulsion, it would be in the direction of r. So this is how, if we would change scale, the farther away it goes, it would be in this direction, but increasing in its magnitude, right? The farther away it goes. So this is why it would be kr, because it would be directed in the same direction, and actually in the same direction, not oppositely, but in the same direction perfectly. There would be this kind of dependence in terms of vectors between the force and the position vector. When you consider the question on what really is this driving this accelerated expansion of the universe, there are some hypotheses, and the most probable one refers to something that we refer to, something that we call void's point zero energy, or maybe energy of the void, or something like this. It is even detected experimentally. It's called Casimir effect. And the Casimir effect shows that there is something like energy in void. And this energy in void is causing some kind of pressure, right, against two plates which are very close to each other. This is called Casimir effect. And the Casimir effect is about a situation when you take two plates, maybe some very small, of course, because this is all in the nanoscopic scales, and you put those two plates very close to each other. The closer they are, the more strongly they are brought together. And to account for this Casimir effect, it is due to the situation that you have in any region of space, in void actually, when you talk about void, it's void only classically. But in quantum mechanics, what you need to do with void is you need to know that void classically refers to the medium of the propagation of electromagnetic waves, because this is light. Light is propagating through void and not within any other material origin. So no any other medium is used to propagate light. And light is understood as the oscillation of electric and magnetic fields. So it's an electromagnetic wave, which means that it oscillates, electric and magnetic fields oscillates in void. And since void is no medium other than just void, it's empty space, then it must mean that really void is this oscillation of electric and magnetic fields. And therefore, void can be referred to as the oscillation or oscillator of electromagnetic fields. And in quantum mechanics, you need to quantize oscillator, and the solution, mathematical solution for quantized oscillator, is that it has a ground energy level. So the ground energy level refers to the lowest possible energy, which is non-zero, but has certain value. So it means that you cannot have actually void which is truly empty. It will always carry certain amount of energy. And this energy is also visible in terms of Casimir effect, is manifesting in terms of Casimir effect, because what follows from this energy, the quantum energy of void, is in terms of quantization, it is referred to as virtual particles being created and annihilated in this region of void, in quantum void. So the void is not really empty in quantum understanding, but it's full of virtual particles appearing and disappearing in the processes that we refer to as virtual particles creation and annihilation. And within these virtual particles creation and annihilation, which is going all the time, all around in any region of empty space, we can put these two plates together, which would be close on a distance comparable to something that we refer to as the de Broglie wavelength. The Broglie wavelength is some characteristic magnitude of dimension that corresponds to matter wavelength that manifests interference and wave-like nature of material particles. It is also close to quantum effects that matter shouldn't be considered in true nature of matter as corpuscular phenomena with trajectories of particles and so on. This is just done in terms of discretization of certain physical quantities such as energy and so on, that they are well-defined packages, let's say, or discrete, but not for the position of particles which start to be, smeared around the space, like they would be replaced by something more like cloud of probability. So wouldn't anymore provide any certainty in understanding of a trajectory. That would also mean that concept of trajectory would collapse. And that is, this actually refers to something that we know as Heisenberg uncertainty principle. That is something very basic in quantum mechanics. And what this means here in terms of the Casimir effect is that normally in void, when you have these waves of particles, there are no limits for them, and therefore they can all around void be created and annihilated equally with equal probabilities. However, when you have two plates close to each other, like this, you can imagine one plate, another plate, close to each other, then if they are close enough, there would be no space between them for the full wavelength of material particles be placed there. So there would be a lot of wavelengths around these particles, but not really for wavelengths would fit between those two particles. So that would mean that significantly larger numbers of these virtual particles appearing beyond those regions of those two plates, in between those two plates, in comparison to a number of particles still happening up to certain smaller probability in between those two plates. There would be lesser number, smaller number of particles there. And the result would be that there would be a positive pressure of the increasing numbers of elementary particles, of these virtual particles from annihilation creation processes. They would be pushing together these plates even further. And that is something that is measurable. Of course, it's a very small effect. And funny, it's referred to as the biggest empirical discrepancy between theoretical predictions and the force that would be actually needed upscaling to account for the expansion, the accelerating expansion of the universe. This discrepancy is of 100 orders. So that it seems that Casimir effect is 100 orders, not 100 times, but about 100 orders. So 1 with 100 zeros times smaller than that would be required for explanation of the accelerating universe. So this is still the best candidate we have, but there is something really wrong here because it's seemingly many ways too small to account for acceleration of the universe. So that dark energy, therefore, is not really understood what it is. We only know that it must just slightly more than double exceed the balance, the total percentage of matter and dark matter for the gravity to be neglected in such a way that we have currently observed rate of expansion of the universe. And how can we be sure that really this observation is true? Well, it's enough to look on the objects like faraway stars. We refer actually to something that is called as standard candles. These are stars of special spectrum decomposition in the spectrum of light emitted, from which one can know exactly the relationship between its mass and intensity of the radiation it emits, of the electromagnetic wave spectrum, actually light, which is emitted from these stars. And since we know these parameters very well and the relationship between them, when we see stars with certain spectral properties, we can be sure that they can be qualified as standard candles. And therefore, simply by measuring their intensities, we can exactly find their distances from us. And using these standard candles, one can say that the far away, the more far away objects are observed, then the higher are the velocities of getting away from us. And how do we measure velocity? I said that you can measure easily the distance from the intensity due to spectral decomposition of the properties combining together mass and spectral decomposition parameters and the intensity of a star. However, to measure the velocity of the star that emits radiation towards us is by measuring the Doppler effect on the electromagnetic wave which we receive, which our detectors measure. So the Doppler effect is also pretty straightforward. It's when you have two observers and one is emitting, maybe one object is, and you have one observer and one object emitting some wave, then this wave has certain periods, temporary periods and and temporary periods denoted by t, and their wavelengths, which are also referred to as spatial periods. Like I draw a wave here. This one is the wavelength, means a spatial type of period. Spatial, right? In space. Spatial period is lambda. It's a wavelength. Wavelength is lambda, and this is it. While t is temporal period. So it is period in time. And this means when there is propagation with velocity v, then the wave propagates with velocity v, then it is lambda divided by t. The spatial period divided by temporal period gives us the velocity. For light, it would be c equal to lambda divided by t, something like this. And now when we are here, these waves propagates with, for example, these waves that I draw here as lines would represent maybe tops of these waves here. Right, this is it, and they propagate through space with velocity v. So now, when you say that this observer would observe waves coming from a source which is getting away from us, right? What it would be equivalent to is that it would be the same in terms of relativity of where you can fix your reference frame to say that the observer is running away. Is getting away from observer velocity, right? And then what happens? Then if he's getting away, then these fronts of waves chase him. And if v propagation of wave is greater than his velocity, they would pass through him, but with, of course, much larger t temporal period, because second top of the wave will still need to chase him and will cross finally, but it will take more time, right? Quite on the contrary would be if the observer would go towards this wave. If he would go in that way, then he would pass this first front wave and the second wave in very short temporal period. And this temporal period translates to frequency, because frequency ni may be referred to as 1 over t, and that would mean that this is a lambda ni. Also, you can say that you could maybe use omega, which is 2 pi over t, and this is just a question of this 2 pi. So when you take maybe t, so t is equal to 2 pi over omega, right? So here, when you substitute it, what you would get is c is equal to lambda ni, or also c is equal to lambda omega divided by 2 pi. Right, so what comes from that? If you have some situation that a star is emitting, because Doppler effect would refer to, could be applied in both material waves, like, for example, sound wave. Sound wave is the physical means of propagation of sound, but it requires material medium, like is, for example, air. You take a hammer and you hit, let's say, some surface with a hammer. That creates waves of pressure, because when the hammer hits some solid structure, then the pressure, air is locally pressurized, but this pressure will disperse through the air. And when you hit many times with the hammer, you create sound waves. And these sound waves are, simply speaking, mechanically pressure waves that propagate through air, and they propagate through air due to the density of air with certain velocity, such that it would be maybe accounting for about 1,000 kilometers per hour, which is referred to 1 Mach number, at the pressure of air and the composition of air we deal with at the level of the sea, at the sea level. However, for example, in water, the sound waves would propagate many times faster. When you propagate sound in water, it travels maybe with some few or even several thousands of kilometers per hour. So much more significantly faster propagation of sound. The difference here is with the wave propagation of electromagnetic type of light is that it does not have any material medium if it propagates. It propagates simply as the oscillation of of electric magnetic fields, which are properties of empty void itself. And nevertheless, they still account for the Doppler effect, because you can imagine that the star is emitting radiation and it gets away from us. It would be the very same situation that you usually deal with when you, for example, walk down a street and you hear maybe an ambulance on a signal coming towards you. So when it comes towards you, is this effect that is drawn here, that your velocity is, since you can change the velocity between these two reference frames, saying that the one reference frame is moving towards you is actually the same physically that your reference frame is moving towards the other reference frame. It will mean that you will cross these wavelengths, these waves, in higher frequency, right? Because t would diminish, and if t diminishes, you see here the frequency grows. So this is frequency, or maybe this is frequency, and this was angular velocity, but also it's used interchangeably to refer to as a frequency. So whenever you have smaller t, your frequency increases. So what you hear is you hear high frequency, high pitch sound of the siren when the ambulance is moving towards you. But at the moment that it passes you and starts to go in opposite direction, it now moves away from you with velocity. You will immediately hear that the pitch changes and the frequency drops suddenly. And then you see, you hear lower frequency sound, because now it's an opposite situation, like you would be moving away. So extending t, temporal period, means actually decreasing frequency. So this is true not only for sound, but also for light. And the difference is that for visible light, there is, of course, electromagnetic wave has a spectrum, and there are different possible wavelengths for light. But what we refer to as visible light is somewhere between 400 nanometers and 700 something nanometers. It's a visible light spectrum that is perceived by us as colors of light. And in the upper, actually, how these wavelengths transfer to frequencies. Well, we can see here on this equation that c is equal to lambda, or maybe not, c is equal to lambda omega over 2 pi. So actually lambda from this is equal to 2 pi c divided by omega. So wavelength is oppositely proportional to frequency, right? Also for light, because c now here is the propagation of the light wave. So in that case, when you have wavelengths of visible light around 400 nanometers, they are pretty short wavelengths. That means that this is a high frequency of light. And this also corresponds to energy. But just on the margin, I write that Planck constant, actually dash, multiplied by omega is the energy. It could be written also that it is h ni, where h bar is h over 2 pi, and h is the Planck constant. Planck constant, which is very, very small. It's a quantum constant. It's about 10 to minus 34 joule multiplied by second, which is the unit of action. Right, so it's a very small, just to govern that these packets of energy that individual photons, so the quantization of light carries, its in energy of individual photon is hugely small. It's in the order of 10 to minus 34 in terms of joules. So it's a small energy, but nevertheless is emitted. And for light, visible light, when we talk about short wavelengths, like 400 nanometers, this is the scale of something that we refer to ultraviolet, high frequency visible light, which is almost not visible. Usually people cannot see ultraviolet already because it's too high frequency, too short wavelengths, high energy, and our photodiodes in iris, as biological structures of our photoelectric elements that allow us to perceive light, to see it, are simply not tuned in such a way that you perceive such higher energy light. And we cannot see ultraviolet, but also we cannot see infrared, which is another end of the spectrum, somewhere over 700 nanometers, which is lower frequency, on the other hand, smaller energy. And the last color we can see is close to infrared, some red color, right? And the infrared color is again not visible. And these, of course, can be extended up towards higher wavelengths like radio wavelengths, ultra short wavelengths, Wi-Fi wavelengths, for example, the electromagnetic waves that are emitted by routers, maybe phones, mobile phones, and so on. And then for UKF radio waves, then medium radio waves, then standard radio waves that are longer. For UKF, it's about maybe 50 centimeter wavelength and so on. They can be arbitrarily long, but diminishing energy, and they can be also arbitrarily short with increasing energy, like X-rays is also light, but certainly not visible. That is highly energetic and has much shorter frequency that it can propagate. For example, soft tissues, it will be only absorbed by bones, some denser tissues, and this is used to make X-rays photographs or X-rays tomography for looking inside of the body without some surgical procedures. Then higher energy is towards gamma rays, which are hugely energetic single photons of huge energy, which are actually radiation emitted in this annihilation process of particle and antiparticle meeting together. They emit gamma photons. Yeah, and they are also used in true applications, in everyday applications, like for example medical devices such as positron tomography is using annihilation process of matter and antimatter. Very small amounts of radiatively active antimatter glucose, radiatively active glucose is given to patients with undetected some cancer conditions, and the tumors which are very active in terms of metabolism, they take this glucose out from the bloodstream and they use it for energy, but then they accumulate some of the radioactive glucose, which decays in radioactive decay, in such called beta plus decay, which is decaying into protons, decay into positrons, which are anti-particles for electrons, and some counts maybe as well. What is happening when the antimatter is produced from the decay of the radioactive glucose in such tumors is that these positrons, anti-particle for electrons, will very briefly meet their counterparts, which are true electrons, and then they will be annihilations of electrons and positrons, and these annihilations will produce super high energy light, which are gamma rays, and these gamma rays can be detected to conserve momentum. Actually, they will be always emitted in two directions, oppositely, which two opposite directions in the same line, but in two opposite directions, which will be detected then by a ring of detectors around the person through the positron emission tomography scanner. And then from the, actually you could use maybe some drawing. These are detectors, right? There's a patient here, and the detection goes in a certain line connecting two detectors on this ring detector, and they can calculate the delta T. For example, this clicks in T1, this clicks in T2, and you can find what is delta T between T2 minus T1, and you will then see exactly the location at which it happens, because they will propagate these gamma rays with c velocity constant, and you can precisely tell the location at which you have here in this axis, and in this axis you can localize the tumor, which is undetectable in any other way with this emission positron tomography that is using gamma rays as well as the annihilation processes with antimatter for medical purposes. So it has been maybe around for several years already. Right, and what can we tell about this Doppler effect in regard to the distribution of matter and the expanding universe is that is the situation that we observe that for the objects that are getting away from us, we see that the spectrum is diminishing in terms of energy. So wavelengths increase, frequencies decrease, and this means energy decrease. So this is called redshift in Doppler effect. For visible light, it goes towards smaller frequencies, so towards infrared. And for the objects that are far away from us, the more far away from us objects we observe, I mean these standard candles, the smaller the intensity is and more shifted in terms of the redshift of Doppler effect. So it means that the more far away object we observe, the faster they get away from us. And it also happens, which has been verified experimentally within these empirical astrophysical observations, for the objects that are barely visible because they have redshift of their frequency with energy going to zero, so they are barely visible with their Doppler effect shifts of energy, diminishing of their energy, are the farthest away objects that we can see. Meaning that any objects that would be even more far away, hypothetically, would be not possible to be observed because of the Doppler effect going to zero with the energies. So there seems a situation that they get away from us with increasing velocities the farther away they are from us. And what is the reason behind that is it is already confirmed is the expansion of the empty space. Why it is? Because space will expand exactly on the same magnitude by volume of space, by magnitude of distance, metrics of distance in space, which would be consistent with the fact that this Casimir effect and the zero-point energy due to quantization of void towards this, we would say, quantum void energy of those virtual particles bustling all around empty regions of space would be constant. But then when you have increasing amounts of space separating us from distant objects, the more space you get, the more space will expand. And therefore, overall, we will have accelerated expansion. Then this accelerated expansion will produce even more space, which will expand at each region with a constant magnitude of expansion. But since it will be more of the space and increasingly more of space, overall, the expansion rate will also accelerate. So this is a conclusion that we deal with, that perhaps in nature this force really does exist, but certainly not a simple classical force. It's more like this Casimir effect and annihilation creation processes combined together, which maybe physically can be modeled like that. However, physically for oscillators, actually this Casimir effect and void, as I mentioned, quantum energy has also a lot to do with the oscillation. So normally what we do with the oscillation, the third, is that we use F minus KR force, which is called restoring force. And since we are already meeting limits of our lecture for today, we started somewhere around maybe 20 minutes after 3, and it's already close to 5. So certainly we won't be able to solve the oscillation. Actually, it's called harmonic oscillator. And therefore, we will leave that out to another lecture. So today we made some comments. So they may be to some extent important, of course, for contemporary physics and understanding of our reality, but somewhat, falling maybe out of the formal considerations that we need to do. So that means that we will need to postpone them, but nevertheless, it's kind of problematic to some extent because we have not many lectures as we're meeting. Well, I believe once every 2 weeks. And that means that to some extent we'll need to simplify our considerations, formal considerations. But maybe it is for benefit of understanding of that all. So let us continue on the next time we meet with solutions, formal solutions of harmonic oscillator, maybe in some somewhat simplified consideration. And for today, I would like to thank you for your attention. If you have any questions, and please do ask them. I'll try to be more explanative about some concepts that maybe are not properly covered so far. So thanks again for staying here on the lecture, and I wish you all the best for the coming time, and see you the next time we meet, probably in 2 weeks. Thank you very much.
Thank you. Have a good day. Thank you. Goodbye.
Thank you very much. Bye-bye.